for the second side of our notes, we're now going to do a full-blown confidence interval. I just showed you guys how you can use the data that they give you to do a confidence interval. And so now we're going to do a full 4-step process of it. So here's the example. Using the population distribution of GPA versus ACT for a small high school in California, I selected the following random sample of 9 students. Now find the least squares regression line for this sample data. So what we're going to do is go back to our calculator. There we go. And I'm just going to do this in one of the calculators. So in the calculator, I'm going to go to Stat Edit. Actually, let me clear all those out. List 1, I'm going to put all the GPAs. 3.7, 2.3, 4, 3.8, 3, 1.8, 2, 2.3, 3.9. And then I'm going to put ACT in the list 2. So 23, 20, 35, 33, 22, 13, 17, 20, 29. And we have to run the least squares regression line on that to find the least squares regression line. So we hit Stat, scroll over to Calc. We're going to calculate the least squares regression line, which is option 8, linear regression. And remember, this one specifically asks for it. This calculator, you have to tell it you want list 1 as your explanatory comma, list 2 as your response. And that's really all you need. You can store your Y bars if you want to, but we don't have to do that. So I'm going to hit Enter. That gives me the A, B, R squared, and R. But really all I'm curious about is the A and the B. So as you guys can see, the A is 1.20139. The B is the slope, 7.50699, whatever. Okay, so we're going to go back to our notes, and we're going to fill that in. So remember, we're predicting the ACT score. That's our response, using the GPA. So we have the A in the calculator is 1.201 plus the slope, which is the B, 7.507 times the GPA, which is the slope. So that's how you would write the line. So we're going to go ahead and write this to do a full confidence interval. So a 95% confidence interval. I've pre-written out a lot of this. You guys can pause it and rewrite it if I'm going too fast. But remember, we have to start with state. I gave you the blank template. We want to estimate the true blank of the context blank at a 95% confidence level. So in this case, we want to estimate the true slope, which is beta, of the population regression line of GPA versus ACT at a 95% confidence level. So that's how we would fill these out. We want to estimate the true slope of the population regression line of, and then just put the context of whatever 2 variables you have, at a 95% confidence level. Now remember, the plan is where we check the conditions, but we also have to have a name for the test. Here's what we call this one. It's a T interval for beta. That's what we're going to call it, a T interval for beta. Okay, I know you can probably already see some of the conditions written lightly in there, so I'm going to go one at a time. Again, this is good practice checking the conditions. So we start with liner, L. Is it linear or not? So I'm going to go back to the calculator and make sure that it's linear. I'm going to look at a scatter plot of list 1 and list 2. So there's a scatter plot. I have to say list 1, list 2, and I'm going to hit zoom 9. There's my scatter plot. Does it look linear to you? I'd say so. It looks like they're all heading up in a positive direction. So I would say for linear, the scatter plot of ACT versus GPA is fairly linear. And then next to it, I would draw a little bit, it does kind of have a little bit of a curve to it, but draw kind of a rough picture of that to show that you have indeed checked it. Second one, independent. Well, 9 is less than 10% of all the students at this school, and we should probably also squeeze in, I don't know why I don't have it in here, that random sample, because we took a random sample. So random sample ensures independence. Okay, or independent samples. How did I say it the other day? Random sample ensures random sample ensures that individual observations are independent. So I'm okay if you just say it like that. Random sample ensures independence. All right, the next condition is the normal condition. So in order to check the normal condition, we want to look at either a histogram of the residuals or a normal probability plot of the residuals. So let me go back to the calculator. To do the residuals, now thankfully we already ran the least squares regression line on here. Remember, we ran linear regression. As long as you run this, it stores the residuals in there for you. So I need to plug the residuals into my list. So I'm going to come up here. Remember that it's stored right here where it says lists. So we go second list, scroll down till you get to the residuals. Those are your residuals. They're already stored in there. If you hit enter, they put all the residuals in there for you. So I want to look at the histogram of the residuals. So to do that, I'm going to go second stat plot, change it to a histogram of list 1. Okay, so I'm going to go zoom 9, and again, you don't ever want to use the window settings that they use, so I'm going to go here. They have 1.8, maybe we'll go to 1, and then how about to 5 with a scale of 0.5, or maybe just 1. Not 0.1, but 1. Okay, let's see how that looks. So to me, that looks pretty normal. I mean, it's got a slight skew, but there's no outliers. It looks pretty darn good to me. So what I'm going to do is come over here, and I'm going to say normal, the histogram of the residual showing that I mentioned what type of graph I looked at, shows no outliers or strong skewness. And again, you want to kind of draw a picture of what you did there. So here's kind of a picture of the graph I have. I proved that I looked at the residuals. The next condition is equal variance. We need to look at a residual plot. So here's a reminder of how to do a residual plot. Go back to the calculator. A residual plot is a scatter plot with the explanatories as your x and the residuals as your y. So remember, we have the explanatory in list 1. We have the residuals in list 3. So I'm going to do a scatter plot of list 1 against list 3, which is the residuals. So all I got to do is zoom 9 there, and there's your residual plot. As long as there's even scatter, which to me there looks like even scatter, that's what we need. So again, I'm going to come back over here, and for my equal variance, say residual plot shows random scatter around the residual equals 0 line for all values of x. Use that kind of wording. Drawing a picture, you want to draw that residual line, that's your y equals 0 line, and just kind of sketch that it is indeed kind of some random scatter. Sketch a picture of it. Okay, option 5 is random. Well, did we take a random sample? We did. We took a random sample of 9 students. So there's my conditions. My conditions have been satisfied. All right, so now we're going to come here and do the do portion. Remember that the do portion is the statistic plus or minus the critical value times the standard deviation of the statistic. So we're going to go ahead and put in the statistic, which in this case is B, that's the slope, plus or minus, I told you on the other side, T star is the test statistic we're using, times the standard deviation of the statistic. I said use the standard error of the slope. So we are going to plug in the statistic. Well, what was the slope? If you look back up here, we ran the least squares regression line. The slope was 1.201. No, that's the y-intercept. The slope is 7.507. Okay, so we're going to take the slope of 7.507 plus or minus the t-star, which we have to get from our paper. Well, remember, I took a sample of 9 students. So if I took a sample of 9 students, we're going to use the degrees of freedom of 9 minus 2, which is 7. So I'll remind you, we look here. We're doing a 95% confidence interval with the degrees of freedom of 7. Okay, go up and over 2.365. So that's going to be the t-star that we use. 2.365. We have the degrees of freedom listed. Okay, so I had to go back and look at what the standard error was. I was confused at what spot we were using. So it's not the one above that I kind of showed above, because that's a different example. I actually put the Minitab output for this example in your next page of notes. So you're going to want to actually go over to your next page of notes here. So this is at the top of tomorrow's notes, but this is the Minitab output. So they have the slope listed, and then here's the standard error, 1.29. So that's actually what we're going to be using, is the 1.29. So the standard error is 1.29, and now all we have to do is multiply it out. 7.507 plus or minus the t-star that we already found times the standard error of 1.29. You get 3.05085. I went up quite a few decimals. And then if you subtract the margin of error and add the margin of error, you get a confidence interval starting at 4.456 to 10.558. There is your confidence interval. So remember, you got to have the full general formula, specific formula, show your work, as well as have the degrees of freedom listed. And finalize with a conclusion, which is the template that we've always used before. We are blank confident that the interval from captures the true what? So we are 95% confident that the interval from 4.456 to 10.558 captures the true slope, beta, if you want to put that in parentheses, of the population regression line for GPA versus ACT. We're basically just recopying what we used as the context above. So there's your first full four-step confidence interval. Okay? I went through all of the conditions with you guys again, checking all of the graphs. But remember, majority of the time, you guys are going to have the Minitab available. Okay, I just didn't have it available on that sheet of paper. I probably should have put it at the bottom. But tomorrow, I'm going to do the exact same example, but we're going to do a significance test of it. So see my video tomorrow for significance tests. Okay, have a good day.